Okay, welcome everybody to this session on learning in games. We have a lot of exciting talks coming up. Before we get started, some quick logistics. I will hold up these placards for the speaker when it's 5 minutes, 2 minutes, and 0 minutes remaining respectively to ensure we stay within time. And depending on time after each talk, we'll have some time for questions, and I'll hand over the mic to anyone who wants to ask a question. So we'll start with the first talk on Fast and Furious Symmetric Learning in Zero-Sum Games by John Lassarsfeld.
Okay, great. So this paper is called Fast and Furious Symmetric Learning in Zero-Sum Games. So this is a joint work with Yorgos Pilioris, Ryan Sim, and Andre Wibisono. The title of the paper is a bit crazy. So to start, let me just in one slide kind of give you some overview of what this talk is about and actually like what the contribution is. So, we study this classical algorithm, fictitious play, for learning in two-player zero-sum games. So, while this algorithm is very simple and kind of dates back to the 1950s, it's actually surprisingly difficult to analyze. And so there's been relatively few things that people have been able to prove about it in the zero-sum game setting. And so kind of the main contribution of our work is to make some progress in this direction. So in particular, we prove for this class of high-dimensional rock, paper, scissors matrices that fictitious play using any tie-breaking rule has square root t regret. And so for those familiar, this kind of establishes a new class of matrix for which Carlin's fictitious play conjecture holds. So the plan for the talk is to just give a little bit of a refresher on the learning in zero-sum game setting, to give more background on fictitious play and kind of the context for the results, and then give some brief high-level intuition for some of the techniques. Okay. So let's recall this online learning in zero-sum game setting. So, okay, we have a payoff matrix A. For simplicity, we'll assume it's a square n by n matrix. And so over a sequence of capital T rounds, two players choose mixed strategies, xt1 and xt2. These are just distributions in the n-dimensional simplex. And so the players, they receive some payoff, and then they also observe the following vector feedback. So player 1 observes the vector axt2, and player 2 observes minus a transpose xt1. And in this setting, players individually try to maximize their cumulative reward. And so of course, this is equivalent to saying they want to minimize their individual regrets, which are the quantities reg1 and reg2. But so in this work, we're sort of interested in understanding the growth of the total regret. We'll just call that regret moving forward. So this is just the sum of reg1 and reg2. And of course, there's this kind of classical connection in the zero-sum game setting between regret minimization and convergence to a Nash equilibrium. So recall this kind of classic folk theorem that says that if this quantity reg t is kind of sublinear in t, then the time average iterates of the two players converges to a Nash equilibrium of the underlying game at a rate of reg t over t. So kind of in general, we're sort of interested in this, in these convergence rates to a Nash equilibrium, but in this work, we'll sort of quantify that by trying to derive these sublinear regret bounds on reg t. Okay. So the algorithm that we study for this is this classic fictitious play method dating back to the 50s of Brown. And so how does this work? So at every time t plus 1, both players choose the distribution that sort of best responds to the sum of the observed feedback vectors through round t, so through the most recent round. And just let me point out that, given the sort of linear nature of these objectives, we assume here that this argmax operator kind of encodes some tie-breaking rule that also always returns like a point mass or a vertex of the simplex. And so equivalently, fictitious play can be viewed as what happens when both players individually use this online learning algorithm called follow the leader, which again is just sort of like the best response to the sum of the previously observed feedback vectors. But so, you might be familiar with the fact that kind of in general, under adversarial reward sequences, fictitious play and follow the leader in particular actually fail. So in particular, we have these examples of adversarial reward sequences where follow the leader can actually have kind of linear regrets. And of course, this is because, because of the greedy nature of follow the leader, its iterates can kind of lack this stability. But I guess the point is that in zero-sum games, the reward sequences that are observed by the players are not necessarily adversarial, and they're not necessarily kind of this worst case in nature. And so this kind of has led to a natural question, which is to ask, can algorithms like fictitious play, which are sort of not no-regret algorithms in general, but can they still obtain these sublinear regret bounds in the kind of more benign zero-sum game setting? So actually, the answer to this question is in fact yes. And this was actually proven all the way back, again, in the early 50s by Robinson, where she showed that fictitious play in all zero-sum games indeed has sublinear regret. But with this upper bound on the rate that kind of scales like very close to linearly, so kind of t to the 1 minus 1 over n. But actually then, a few years later, there was this conjecture of Carlin, who conjectured that actually the true rate for fictitious play on all zero-sum games is to have regret scaling only like square root t. So basically, like for the next 50 years, there was like no progress on this conjecture until a result of Daskalakis and Pan in 2014 that showed the following. So they actually came up with a lower bound construction on the n-dimensional identity payoff matrix, showing that the regret of fictitious play on this example indeed actually scales like this nearly linear rate, matching the upper bound of Robinson. But in particular, this sort of relied on using in their proof like an adversarial tie-breaking rule. So sort of in contrast, a more recent result a few years later of Abernathy, Lai, and Wibisono showed something a bit more positive. So actually they showed that if we instead use a fixed lexicographical tie-breaking rule, then fictitious play on all diagonal payoff matrices, so including this identity payoff matrix, fictitious play actually has this faster square root t regret bound. And so, besides these two results, it's kind of remained open whether we can establish, similar fast rates for fictitious play on other classes of payoff matrices, kind of under various tie-breaking assumptions. And so again, like the main contribution of our work is to make some new progress in this direction. So again, what we show is that on this class of n-dimensional rock, paper, scissors matrices, under a certain symmetric learning condition, that fictitious play using any tie-breaking rule has square root t regrets. So just to unpack this a bit, what are these matrices? Well, these are sort of the generalization of the classic three-strategy rock, paper, scissors game to a sort of weighted and high-dimensional regime. And in particular, this is sort of the canonical symmetric zero-sum game where, that just means kind of, it's a little bit of a misnomer, but these are skew-symmetric payoff matrices. So then for these skew-symmetric payoff matrices, the symmetric learning setting is this setting where we have identical initializations. And the result of this is that it turns out that all remaining iterates or all remaining strategies of the two players actually remain identical for subsequent rounds, and so it suffices to kind of analyze a single trajectory of the algorithm. And then let me also just mention again is that, in contrast to the results of the previous page, is that we make no assumptions on the tie-breaking rule. And so this kind of establishes a new class for which Carlin's fictitious play conjecture of this square root t rate indeed holds. And let me just also add that as sort of a secondary result, we prove this same square root t regret bound for online gradient descent in this regime of constant step sizes. So absolute constant step sizes kind of independent of the time horizon. And this is sort of what was coined in a prior work of Bailey and Pilioris, like a fast and furious regime. And the core idea that we use to prove these results is to leverage like a certain geometric perspective of the iterates in like the dual space of payoff vectors. So just very briefly, let me just give kind of like a one-slide overview of some of the analysis. As I mentioned, we're interested in studying these dual payoff vectors, or what we call the dual iterates, YT, which again is just the sum of the observed payoff vectors through the previous round. And so it turns out like in this payoff space, which is just Rn, we can define this energy function psi. This is just like the support function over the simplex. And just by definition, it kind of follows that the regret of the process after t total rounds is kind of proportional to the energy of the final dual iterate. And so in order to get balance on regret, it sort of suffices to control the energy growth. And kind of the key underlying property that we leverage is the fact that these dual iterates under fictitious play follow a certain skew subgradient descent with respect to this energy function. And this is kind of similar to properties identified both for fictitious play, but also other FTRL algorithms in several recent works. And the point is that this kind of insight helps guide us in understanding how to control the energy growth of the dual iterates over time. Okay, so I lied, this is actually a two-slide overview, but basically the key property that we then prove is to show that for this class of rock, paper, scissors matrices, the dual iterates exhibit this certain cycling throughout regions of the dual space that holds regardless of the tie-breaking rule. And then roughly speaking, we can show that this cycling helps establish a certain regularity in the energy growth, which then, when we kind of accumulate this over time, leads to square root T total energy, and thus, the square root T regret bound. So let me just end by saying, it's still kind of open whether we can get this same rate for other classes of symmetric zero-sum games, but we think that some of the techniques we established can kind of help in this direction. So happy to answer any questions, but thanks.
Thanks for the nice talk. If you have a question, please raise your hand.
What is the barrier towards generalizing this technique to other matrices?
Yeah, that's a good question. So well, let's just say for skew symmetric matrices, so the key thing that we leverage for the rock, paper, scissors is in fact this very nice kind of structural property of the dual iterates, a certain cycling. So we think this kind of holds, or some flavor of this kind of holds more generally for other skew symmetric matrices, but sort of would, we really need to kind of prove something inductive there, but we think, something similar should hold.
Maybe you can decompose it into cycles, or I don't know.
Yeah, or some hierarchical structure, or things like that, yeah.
I had a very quick question.
Yeah.
Can you, so for the case of, you mentioned you have something for for gradient descent, right?
Yeah.
Can you say anything about the last iterate on that? For online gradient descent, or would you expect the last iterate to cycle even there?
Yeah, that's a good question. So in general, in this fast and furious regime, so these absolute, these absolute constant step sizes. So it's already known in general for zero-sum games that with these absolute constant step sizes, the last iterates diverge towards the boundary of the simplex. So there's nothing we can say about the last iterate, but we can say something about the sort of time average iterates still.
Thank you. Thanks again.
If you could please reduce the spaces to let the people find a seat, please. And there are a lot of seats on the front row here, so if you want to sit down.
Yeah, you're giving the next talk? Yeah. Okay, I think they will, yeah. And you should be able to. I guess the question is, how do you move on to the next slides? How did the previous speaker do it? Sorry, let me just ask them.
Good morning, everyone. Today, I will present our work on decision-making in changing environments, which connects robustness and statistical query learning, and also local differential privacy. This is a joint work with Sasha. So interactive decision-making is a broad area that includes online learning, control, and also reinforcement learning. And recently, there has been a growing interest in understanding, generally, the statistical complexity of interactive decision-making problem, and importantly, the generic algorithmic principle that may achieve statistical optimality for a broader class of interactive decision-making problems. So toward this end, recent work has formalized the decision-making with structural observation framework, which is a generic interaction protocol for interactive decision-making problem. So in this protocol, the decision maker interact with the environments for T rounds, and for each round, the interaction start with the decision maker selecting a decision pi T from the decision space, and observe an observation OT in response for the environment. This is quite a generic interaction protocol. For example, in classical statistics, the observations are identically distributed, which corresponds to the special case where there's no decision to make. And structural bandits can also be class in this framework, where the decision space is simply the class of all actions, and for any action pi, the observation under pi is simply the reward. And also for reinforcement learning in Markov decision processes, the observation is the edge step state action reward trajectory obtained by executing the policy pi. So under this generic formulation, recent work has developed the decision estimation coefficient theory for generic interactive decision making, and I'll call it DEC for short. So basically, DEC provides lower and upper bound for the statistical complexity for a broad class of learning objectives, including regret, pack learning, reward-free RL, and also multi-agent decision making. A key limitation on this DMSO formulation is that it assumes that the environment is stochastic, in the sense that for any decision pi t, the distribution of observation conditional on pi t is fixed and specified by the underlying model M star, which means that the environment is stationary. But there are adversarial settings where the environment may be adaptive, for example, in adversarial bandits. And so to capture this adversarial setting, which is more difficult for decision maker to learn, adversarial version of DMSO is also proposed, where for each round t, the decision maker selects pi t simultaneously as the environment selects an arbitrary model mt, and the observation is drawn for mt pi t. So in this setting, the environment is adaptive in the sense that the model mt can depend arbitrarily on the entire interaction history. However, there are still many important problems lying beyond these two settings, and despite the DEC theory, the success of DEC theory in capturing the exploration complexity in stochasticity and adversarial DMSO, very few are known from the setting that are between these two DMSO framework. And one key example is the statistical query learning setting, where to make the notation consistent, we rephrase the SQ model in this in our language, in this protocol, where for each round t, the decision maker selects a query function vt, and the observation is a real value vt that is close to the expectation of the query function vt under the underlying distribution m star. So in this SQ model, the response value vt can be adversarial, but it must be close to the expectation. And another key example is the robust learning setting with adversarial contamination. So in this setting, the environments may select for each round t a model mt, a slightly corrupted version of the underlying model m star, simultaneously as the decision maker's choice of decision, and the observation ot is drawn from mt pi t, which can be regarded as a corrupted version of the real observation that is drawn from m star. So in these two settings, the environment is adversarial, but with structural constraint. So this makes the learning significantly difficult compared to the stochastic setting, but still easier compared to the adversarial setting. So to capture these settings with these motivations, we propose the hybrid DMSO framework, where the protocol is as follows. Before the interaction starts, the environment may first select a constraint, which is a class of all possible models the environment may select throughout the course of interaction. And during the interaction, the environment selects a model MT simultaneously as the decision maker choice of pi t, and the observation OT is again drawn from MT pi t. Here, the constraint is not revealed to the learner, and it restricts the power of the environment. For example, for stochastic DMSO, the environment always selects the fixed model M star, which means that P star only contains M star. And in adversarial DMSO, the environment may select any possible model, so P star is the class of all possible models. So in general, the constraint P star is not known to the learner, but we formulate the prior knowledge of the learner in terms of a class that contains the ground truth constraint the environment may select. And we analyzed the statistical complexity of hybrid DMSO through the DEC lens. I cannot go into details of the motivation of like a definition of DECs due to the time limit, but the high-level idea of DEC is that, for example, in the main focus of this talk, we consider packed learning. And for packed learning, DEC characterizes the loss decision maker must incur due to the fact that it cannot distinguish two models that are statistically close. And so generalizing the DEC from stochastic DMSO framework, we propose hybrid DEC for hybrid DMSO. And our main result is that the hybrid DEC provide both lower and upper bounds for the min-max risk for any hybrid DMSO problem. So specifically from the lower bound side, we show that for any algorithm, there exists a constrained and oblivious environment such that the algorithm's risk under this environment must be lower bounded by the hybrid DEC. So hybrid DEC really represents a fundamental limit of learning in any hybrid DMSO problem. And from the upper bound side, we propose a generalization of the exploration by optimization algorithm that achieve upper bounds under any adaptive constraint environment, and upper bound scaling with the hybrid DEC, with an additional factor of the log catenarity of the class of constraints, which can be regarded as the estimation complexity, and it can be easily upper bounded for most parametric and non-parametric class by the covering number. And as instantiations, we consider query-based learning, which is a slight abstraction of the SQ model. So in query-based learning, for each round T, the decision maker selects the abstract query phi T and observe a vector response that is close to the M star phi T. So we use this this slightly abstract SQ model where the response is simply a real value, and M star phi is the expectation of the query function phi under the distribution M star. And we adopt this general protocol because it also encompasses the VSTAT oracle, correlation SQ, and differentiable learning queries. So we can instantiate our DEC theory to the query-based learning setting and derive the DEC for query-based learning and also the lower and upper bounds. And what is interesting is that the DEC theory we develop, and specifically the DEC lower bound, in fact recover several different, seemingly different statistical query lower bound techniques. So given that the DEC provides both lower and upper bound for any query-based learning problem, it should not be less surprising that the DEC can be lower bounded by various notions of correlation-based SQ complexity. But what is even more interesting is that it has been known that to characterize the optimal adaptive SQ query complexity, this query complexity is characterized by the randomized SQ dimension. And we can also write down the definition of DEC specialized to SQ learning. While these two definitions look very different, we can show that they are in fact quantitatively equivalent by the minimax Herman. And in addition to the constraint on the adversarial environment, we also consider constraint on the information that the decision maker may receive, with a primary focus on the local differential privacy. So in local differential privacy model, for each round T, the decision maker has to select a differentially private channel in addition to the decision, and the observation received by the decision maker is privatized through the channel. So we can derive the private DEC for this setting, and it has close connection to various other notions of complexity, and we can also derive various new or recover existing results by the DEC theory, with the upper bound achieved solely by the exploration by optimization algorithm. Additional instantiation include robust learning with the serial contamination, and we also identify interesting connections to existing notion of complexity like modulus of continuity, and also the dimension that characterize private learnability. And open directions include the tighter lower upper bounds to close the gap of estimation complexity, and also how can we derive computational efficient generic algorithm. Thank you for listening.
Talk. Any questions?
in the upper bound in terms of the DEC, in the fully adversarial case, where the constraint set is just the entire model class, so the epsilon upper bar has like just that log p is just 1 there. Is that right?
Yes. Oh, like here. Sorry. I guess I made the dependence on the fractional covering number of the decision space, which is generally small. So sorry for the typo. Like, so in general, we also need to scale with the log cardinality of the decision space pi for adversarial setting.
Okay. So it recovers what was known by the 2022 paper.
Yes. Yes.
Okay, let's thank the speaker again.
For the people standing, there are still many seats here in the front row or in the second row. And please do not let any space in the middle, or there are many people still standing. Thank you.
So the next talk will be on base correlated equilibria, no regret dynamics in Bayesian games, and the price of anarchy by Kaito Fuji.
Kaito, thank you. Thank you for the introduction. I'm Kaito from National Institute of Informatics, that is located in the center of Tokyo. And I will talk about Bayesian games and no-regret dynamics. So let me start by illustrating the main idea of this study through a simple game like this. So there are two people who want to go out together next weekend. But they decide their destinations independently. That sounds unnatural to me, but probably that was natural when this game was proposed in 1950s. And they have some preferences over the places. But just keep in mind that it is much more important to choose the same place. That is much more important. The setting we are interested in this study is Bayesian games. In Bayesian games, each player has their own private information that is called a type. And type represents, for example, their personal preference. And each person knows their own type, but doesn't know the other player's type. But the type is generated from some distribution, and that distribution is a common knowledge. So the key challenge here is how we can help the players coordinate their destinations. The solution is very easy, just communication. More precisely, just we introduce a credible third party that is called the mediator. And the players indirectly communicate through this mediator. In the first stage, each player privately tells their types to the mediator, like I prefer the C or something. And in the second stage, the mediator privately sends a recommendation to each player. Here, we have two important incentive constraints. The first incentive constraint is like this. In the first stage, each player has no incentive to tell an untrue type. And the second one is that each player has no incentive to disobey the recommendation. If both these two conditions are satisfied, this recommendation strategy is called a communication equilibrium. Before presenting our results, I would like to explain why I'm interested in communication equilibrium and why it is important. The first remark is this concept combines two important properties, two important concepts in game theory: mechanism design and correlated equilibrium. In mechanism design, like in auctions, each player tells their types under some incentive constraints. But in the second stage, there's no incentive constraints. The mediator decides the binding outcome. On the other hand, in correlated equilibrium, which is defined in complete information games, so there is no type. But in the second stage, that is the same in communication equilibrium. There is incentive constraint. So communication equilibrium combines these two incentive constraints. And the second remark is that the communication equilibrium is a natural generalization of correlated equilibrium to Bayesian games. But interestingly, there are multiple natural generalizations of correlated equilibrium to Bayesian games. And the communication equilibrium is one of them that can be realized by the mediator most naturally. So now let me introduce our contributions. Our ultimate goal is to efficiently compute a communication equilibrium that is good in some sense. Toward this goal, first we show that dynamics minimizing a variant of swap regret that we call untruthful swap regret converge to communication equilibrium. And then we design an efficient algorithm that minimizes the untruthful swap regret with some sublinear upper bound. And we also provide some lower bound on the untruthful swap regret. And to complement, we provide the bounds on the price anarchy from the broad class of games. The price anarchy is a guarantee on the social welfare. Okay, so now let me introduce the formal definition of communication equilibrium. It is a bit complicated, but just to make the concept precise for the people who are familiar with this topic. N is a set of players here, and each player I has their own action set AI and type set theta I. And A denotes the set of action profiles, and theta denotes the set of type profiles. And as I have already mentioned, the type profile is generated from some commonly known prior distribution that we denote by rho. Thank you. And Vi is the utility function for each player I, whose value depends on type profile theta and action profile A. These are standard notations for Bayesian games. Using this notation, we can define a communication equilibrium as a distribution over action profiles conditioned on a type profile. This is a recommendation strategy for the mediator. If this distribution satisfies the incentive constraints, we call it a communication equilibrium. There are two types of deviations. The first one, psi, represents misreporting psi of theta I instead of the true type theta I. And the second one is phi. It represents choosing action phi of theta I AI instead of the recommended AI. If any combination of these two deviations cannot improve the expected payoff of any player, this distribution is called a communication equilibrium. Sorry, it is a little bit complicated. It is not so difficult to generalize learning dynamics to Bayesian games. In each round, each player decides their mixed strategy. This is a distribution of actions conditioned on their own type theta I. And this is a full information setting, so every player can observe the other player's strategies, and they receive some expected reward depending on their older players' strategies. In this dynamics, every player is faced with some online learning problem, but reward vector is a little bit strange. It is defined for each action and each type also. And the type is generated randomly. For this online learning setting, we define the untruthful swap regret, which is a generalization of swap regret to Bayesian games. And if each player minimizes untruthful swap regret, that dynamics converges to communication equilibrium. The definition looks complicated, but still, but again, we consider two types of deviations, psi and phi. And psi represents to tell an untrue type, and phi represents disobeying the recommendation. Thank you. Here, I would like to give a high-level overview of our proposed algorithm for minimizing untruthful swap regret. The definition of this regret looks complicated, but actually, these deviations can be expressed as a single matrix Q, and the set of all possible Q is an explicit polytope. It's still complicated, but still complicated but explicit. Then we can apply the file regret reduction framework, that existing one. So it's already an online convex optimization problem. So it's tractable. But to obtain a tighter upper bound, we further decompose this problem into small expert problems. Putting everything together, we can obtain this upper bound. We also provide a lower bound, which is tight in terms of the number of types. Then I would like to give our results on the price of anarchy. I understand that this is less interesting to the code committee, but sorry, please give me some time. The price of anarchy is defined as the ratio between the social welfare achieved by the worst equilibrium and the optimal social welfare. If you are not familiar with this topic, then please think of the social welfare as just a sum of the players' utilities. If we can obtain a lower bound on the price of anarchy, we can claim that the outcome obtained by the no-regular dynamics is the approximately socially optimum. Here we introduce some observation. That is, the dynamics actually converges to communication equilibrium with some good property. Using this property, we can extend existing price of anarchy bounds to the outcome obtained by our no-regular dynamics. So I would like to finish my talk by showing this as the summary of our contributions. That's all. Thank you for listening.
Thanks for the nice talk. Maybe we have time for one question.
Yeah, so in mechanism design, there are some very strong negative results, right? About like, in a lot of situations, impossible to design a mechanism in which there's no incentive to lie about your type. And usually I know that they're circumvented by assuming that there's some kind of bidding, so there's some kind of transferable utility or something. Whereas here it seems like you claim that there's always an equilibrium, right? So are those two things reconciled?
Sorry, I'm not so sure about that question, but probably in mechanism design, they aim at some optimal mechanism, right? Always they need some guarantee about the social welfare. But in this setting, I just said it is possible to obtain some correlated communication equilibrium. So that can be like just trivial mechanism, just like any trivial mechanism. So it is not interesting in the mechanism design context, I think. Does that answer your question?
Yeah, thank you.
So sorry.
Okay, let's thank the speaker again. Next talk is by Yue Wu on instance-dependent regret bounds for learning two-player zero-sum games with banded feedback.
All right, thank you for the introduction. Hi, everyone, good morning. My name is Yue Wu. I'm a PhD student from the University of Southern California, and today I'm presenting our paper titled Instance-Dependent Regret Bounds for Learning Two-Player Zero-Sum Games with Banded Feedback. This is a joint work with Shinji Ito, Haipeng Luo, and Tara Tsuchiya, and since this is quite a long title, I'm gonna introduce it bit by bit. Now, let's start from the single keyword that is most important in this room, games. Self-play dynamics in games has occurred in a lot of different areas of AI research, from beating human in playing poker, to using GANs to generate images, to aligning large language models. In these kind of settings, we can always find a model where two or more players are playing a game repeatedly, and they're all using some kind of algorithm like gradient descent to decide their strategies. The most obvious example being training GANs here. And since from any single player's perspective, it is a online learning setting, we know that results from the online learning theory shows that if all players use some kind of algorithms like MWU, we can achieve a regret that grows like square root of t. Now, this regret bound has been improved in recent years quite significantly, at least in the game setting, to O log t in general games and O1 in zero-sum games. However, both of these results assume one thing in common. They assume what's known as the gradient feedback. For something like gradient descent, you obviously need a gradient. And in the game setting, this means that no matter what the player play, they will always get to know the payoff for every single action, no matter it's chosen or unchosen. And this is often unrealistic in a lot of real-world scenarios, where you may only get to know the payoff for the action you actually choose, and even worse, this action can contain a noise. This is known as the bandit feedback setting, similar to multi-arm bandits. Now, the very unfortunate thing is that under bandit feedback, it is impossible to optimize beyond O root t, even in the simpler case of zero-sum games. So this has been a significant barrier of research. But if we look at multi-arm bandit literature, there are some ways that we can tackle this. So taking inspiration from MAB literature, we know that even if root t is not improvable in the worst case, algorithms like UCB can achieve what's known as instance-dependent regret, where the dependence on the time horizon is logarithmic, but in addition, it also depends on the specific instance of the bandits. Here, it depends on the gap between the arms. So our main problem that we try to tackle in our paper is it possible to get something similar in the game setting? Can we get some kind of instance-dependent regret bound for self-play, bandit feedback self-playing games? And since I'm already standing and presenting here, the answer is yes. Very conveniently, our algorithm also works in the worst-case setting, recovering the same worst-case bound. Okay, let's start with the setups. So there is a game. We assume that there is a game, a zero-sum game, represented with a matrix A that both players do not know. Now, in order to gain some information about the matrix, they have to play it. So in each round, they try to decide a strategy, which is a probability distribution over a finite set of actions. Sorry, and they each draw an action from this probability distribution, I and j, and play it. Now, the first player, the X player, receives a reward that is equal to Aij plus a zero mean noise, because we're in a bandit feedback setting, and the reward for the second player is the negative of that number. At this point, only the reward is revealed to the players. The players will not get to know anything else, including, for example, the strategy or action of the other player. And this process just repeats. So here's a list of our notations that I've shown in the last slide. To measure the performance of an algorithm, we use the very standard notation of the regret, which is the accumulated payoff of an algorithm compared to the best single action in hindsight. And since we're dealing with a noisy environment, following multi-arm bandit literature tradition, we are comparing expected payoffs, so this is pseudo-regret. And since we're dealing with a zero-sum game, as another presenter has already shown us, if the regret is sublinear, then the average trajectory converges to an approximate Nash equilibrium. All right, and the algorithm we use is fairly simple. Actually, it's off the shelf from the multi-arm bandit literature. It's called TALIS-INF. For those who are not familiar with the concept, it is an instance of the FTRL framework, which means that in every step, it is best responding to the past payoffs with a regularizer, so making it not so extreme. In the formula above, L hat of S is the standard importance-weighted estimator of the gradient, which also occurs in, for example, EXP3. Phi of X is the 1/2 Tallis entropy regularizer, which is a fancy way of saying sum of square roots. And eta t is the learning rate, which is equal to 1 over root t. With this algorithm in the multi-arm bandit literature, we know that it achieves what's called as best of both world optimality, which means that in the worst case, in an adversarial setting, it achieves the optimal worst case regret, and in a stochastic setting, it achieves a optimal instance dependent regret. Now, in a zero-sum game, it is very natural to assume that since the other player is playing completely against our incentive, it is somehow similar to the adversarial setting. However, as our result shows, we do have some kind of instance-dependent regret. So here's our main theorem in a very informal way. In the bandit feedback self-play of Thales inf, we know that the regret is always bounded by the sum of two terms, a log t term and a square root of t term. And both constant factors here, C1 and C2, depends on the game matrix. The first term, C1 log t, can essentially be seen as the cost of eliminating the non-Nash equilibrium actions, which means that it is small when the payoff gap between the Nash equilibrium and the non-Nash equilibrium action is large. The second parameter, C2, represents the difficulty of finding the Nash equilibrium within those support actions. It is first always bounded by the square root of n plus m, recovering the worst case bound. And it can be much smaller, especially when the Nash equilibrium has a small support or close to a unit vector. Now, we do need to note that even in the instance-dependent setting, root t growth of the regret is unavoidable unless the game has a unique PSNE. To validate our result, we performed numerical experiments. So we constructed a game that, according to our formula, C2 grows at a rate of t to the minus 1/6. This implies that Thales inf has a regret growth rate of t to the 1/3. In comparison, EXP3 has the worst case regret bound of t to the 1/2, and UCB is unfortunately linear because it doesn't work in adversarial settings. And the simulation experiment result aligns with our predictions pretty closely. Now, as I have said, it is impossible to optimize beyond root t unless you have a PSNE. So in the very important case where you do have a unique PSNE, we can improve our bound to only a log factor. Here, the factor C1 is the sum of this also the sum of two terms. Looks like this formula. And if we compare it to MAB, it looks very similar to what you would get if two players are each individually playing a stochastic multi-arm bandit against the other player's any action. This generalizes the previous result in dueling bandit, which in our notation will be a skew-symmetric zero-sum game. And we also provide a matching lower bound, showing that our algorithm is optimal. Thank you. Now, a regret bound only shows the average iterate convergence. It turns out that this algorithm, Thales inf, also converges in the last iterate. It converges to the Nash equilibrium at a rate of 1/root t, measured by either expected duality gap or expected Bregman divergence. This improves a previous result of t to the minus 1/6. However, we only work on zero-sum games while they work on general games. And as an application, our algorithm can also be used to identify the PSNE given a single action sampling oracle. But just by running and repeating our algorithm for a certain number of times, the exact number depends on the matrix. We can identify the PSNE with high probability with a sample complexity that looks like this. Now, this problem has been solved optimally by MIT et al. However, our algorithm is a no-regret learning dynamic, while their algorithm is an uncoupled algorithm, which means that two players need to cooperate and suffer a larger regret. So as a conclusion, some zero-sum games can be learned under bandit feedback more efficiently than the worst case bound. And just by using a simple algorithm of Thales inf, we get regret minimization, last iterate convergence, and a simple way to find the PSNE. We do have some interesting future directions, but due to time constraint, I guess I'm just gonna leave everyone at this slide. If you're interested to look at the paper, here's the QR code, here's my contact, and yeah, I guess that's it. Thank you very much for listening to my talk.
Thanks for the great talk. Any questions?
Thank you for the great talk. I wonder if the square root t factor is necessary in the instant dependent sense.
Yes. Formally, if we know the game matrix is in some neighborhood of another game that does not have a unique PSNE, then this root t regret is unavoidable, even in the 2x2 matrix. So if you're playing two-player matching pennies or something that is very close to two-player matching pennies, then it's not like root T is unavoidable.
Okay, thank you.
Yeah.
So for the PSNE identification, do you need to know that there is a PSNE in this game and then find it?
Yes, we assume that the game has a PSNE and then find it.
Okay, but could you derive also an algorithm that tries to guess if there is one or not, or?
So in our algorithm, we actually just return, we basically just return the most played action. And I believe if we run it for enough times, run it for long enough, and we can observe that, for example, if there is a PSNE, if we run it for long enough, then 99% of the actions played then will be concentrated on one of them. So if that's not the case, we can probably conclude that we do not have a PSNE, but this is just top of my head.
Okay, thank you.
Thank you.
Okay, I had a question. Oh, no, I'll ask mine offline.
I mean, that's kind of a continuation of what she was asking. I think an appropriate question to ask rather would be if you have a, we know that matrix always has a Nash equilibrium, so what is the optimal complexity to find an approximate Nash equilibrium? That would be an appropriate question to ask. Instead of asking whether the game has a PSNE or not, a much general question to ask would be okay, given a matrix, can you find an approximate Nash equilibrium?
Approximate PSNE or
no, Nash equilibrium.
I believe...
In an instance-dependent fashion.
I believe it is also hard, as in root T regret. But
so ideally, so when I'm thinking in terms of sample complexity, you'll have two terms. One would be some 1 by epsilon square, and then some instance-dependent term. But ideally, in worst case, it is n by epsilon square, where n is the number of rows. But ideally, we would like to bring it down to something like k, where k is the size of the support. So do you think something like this is possible?
At least not with our algorithm. We have done similar numerical experiments on this kind of setting, and we did conclude that at least not by Salas-Inf.
Okay,
yeah.
Cool.
Thank you for the question.
Okay, let's thank the speaker again. Here from Yuval Dagan on the computational intractability of strategizing against online learners.
Hey, okay. It's a joint work with Angelos Assos and Nived Rajaraman. Sadly, they couldn't come, so I'll be giving the talk. Normal form games, probably most of you know about it. It's just a two-player game. Each player has a finite set of actions. Each player selects an action and then receives a reward for this action. For example, rock, paper, scissors. Each player has 3 actions. And then let's say the winner gets 1, loser -1, and then tie is 0. And zero-sum game is when what player 1 wins is what the other loses, like in poker or rock, paper, scissors. General sum games are more complicated game that, for example, in auctions, it can be the case that it's not necessarily one wins what the other loses. So there are many examples. In this talk, we'll talk about repeated normal form games between 2 players. So in each round, both players take an action, and then it just repeats. And motivated by the fact that in many cases, players use learning algorithms to play games, we ask what can the other player do if one player is using a learning algorithm. So let's see the setting. So there are two players, a learner and an optimizer, and in every game they play an instance of the game. For example, the game here is, in the example, is when a seller offers a price and then a buyer decides whether to buy the item or not. And the assumption is that the buyer is using some learning algorithm. Maybe every time it receives the item, it checks how good it is and updates its preferences. And the seller should be a bit smarter. So the seller knows that the other player is using a learning algorithm. So it tries to mislead the buyer. So, well, we can think of better scenarios, but so here, like the seller will just try to get as much as possible from the buyer, and if the buyer is using a learning algorithm, the seller is kind of tries to make it pay as much as possible. So it's a kind of a fruitful line of related work. There are many papers. For example, John Schneider, that is here, he has like a billion papers about it. Like maybe all the papers, almost, except this one is with John Schneider. Anyways, so for zero-sum games, like it's just trivial that when a player using a no-regret learning algorithm, it's like average utility, like basically it can get as much as what you would get in min-max equilibrium, which is like the best possible thing. So against zero-sum, the optimizer cannot do much, but in some games it was shown that the learner, the optimizer, the smart guy, can actually get more than what it would get just because of how the learning algorithm behaves. And it was studied in specific games also. So many specific instances were studied where we have a learner and the optimizer tries to maximize its utility and efficient algorithms were found. But the general case was still open. So in this paper, we ask what happens if we have a general sum game that is played repeatedly and one learner is just using a standard learning algorithm. For example, so we study multiplicative weight update, which is a standard learning algorithm. And we ask whether there is a polynomial time algorithm for an optimizer to plan how it behaves in order to maximize the overall utility after t rounds. So so that's setting in more formality. We have a learner. It's everything about the learner has some L on top, and the optimizer will have O. The learner just plays multiplicative weight update. Basically, what it does at every round, it looks at which action gives the best reward on all the history, on all the history actions of the optimizer, and it approximately chooses the action that maximizes its utility on past actions. And the optimizer can do whatever, just wants to fool the learner to get as much utility as possible. Yeah, so that's the setting, and that is the theorem. So the theorem says that basically it's NP hard. So we assume that some time horizon t, and some each player has an action set that is polynomial whose size is polynomial in t. It can be t to the epsilon for any constant epsilon. The reason why it has to be polynomial is because like we reduce to NP, and otherwise like we would not be able to to do the reduction. And yeah, so up to omega of t, it's not possible to find an optimal strategy for the optimizer. Okay, so we reduce. So that's for the theorem. Now let's look at the proof idea. So we reduce to a weighted traveling salesman problem. And in particular, what's the weighted traveling salesman problem? So you have a graph, fully connected graph, and each edge has a weight of either 1 or 2. And the goal of the player, the optimizer, but in weighted graph is just like a traveling guy that is to visit all the vertices of the graph while maximizing the sum of utilities. So it's a Hamiltonian. It has to go like visit each vertex exactly once and maximize the sum of utilities. Usually it's viewed as minimizing the sum of costs, but here we view it like this. And up to omega of 1 multiplicative factor, this problem is NP hard, so we will reduce from this problem. And basically, we want to construct a game such that an optimal strategy for the optimizer will yield a solution to this TSP instance. And this shows that it will be hard. And basically, we will construct a game such that the optimal thing for the optimizer to do is to just play, so you have t rounds and n vertices, so the path has to be of length n, so the optimal thing would be to play each edge, so the actions of the optimizer will be the edges, the optimal thing would be to play each edge for t over n times, according to, and the edges should be according to the maximum weight Hamiltonian cycle. Okay. So this is like general proof, not proof, like just like idea of how the reduction goes. So yeah, so I said the optimizer plays edges of the graph. And somehow we make it so that in the beginning, the optimizer, like by modifying the game a bit, so we make it at the beginning, the optimizer will have to play an edge that starts at V1, otherwise it will get no utility. And that's because we somehow make sure that the learner starts by playing a specific action. And this action only gives reward to, this action that the learner will play will only give reward to the optimizer's action that starts from V1. Okay, so the optimizer plays V1, but if it will play V1 too much, then somehow it will activate bad actions for the learner. Oh, it's 0. Oh, I haven't seen that it was 2. Okay. Anyways, so there are many details to this reduction, but basically it ensures that it plays across the Hamiltonian path, and everything that deviates from it will not be good for the optimizer. Okay. Wait. Okay. Yeah. So there are some open problems. Yeah, we show NP hardness via reduction. So you can read it. Well, yeah.
Thanks for the great talk.
Hi, thanks for the talk. So what will happen if the learning rate for the MWU is constant? For example, like a fixed number, 0.01 or something?
Oh, if it's constant, then you can always, oh, you mean to compute the optimum?
Yes.
We haven't thought about it. possibly it will also be, well, if it's constant, maybe you just make the utilities really, really small. So then it will change. So if the utilities of the learner will be so small, then even a large learning rate will simulate the same behavior, maybe. But yeah, we haven't considered it.
All right, thank you.
Okay, in the interest of time, we'll move on to the next talk. Thanks again for the great talk. Okay, the next talk will be by Guy Karnowski on the Oracle complexity of simplex-based matrix games.
Okay, yeah, hi, thanks for sticking out in this nice warm weather. A disclaimer is that I don't know a lot about game theory. I'm not a game theorist, but we started this project, a project of mine with Ohad, who's my advisor, from the perspective of learning theory and optimization, and it turned out to have some implications on game theory, which I guess is why I'm in the session. Okay, so what are simplex-based matrix games? So they involve three components, a matrix, n by d matrix, and we imagine n and d to be quite large in our context. The probability simplex in n dimensions, and a domain, a convex domain, a d-dimensional domain. And a matrix game over the simplex is simply the bilinear minimax optimization problem. So we're minimizing over the simplex, maximizing over W, the bilinear form corresponding to A. Okay? And this is an extremely fundamental problem and very well studied throughout machine learning, statistics, economics, operation research, because it turns out to encapsulate, depending on the geometry of W, many very well studied and important problems. And we'll talk today about two canonical examples. So denoting by gamma the optimal value, one way to interpret this is just finding a linear separator. So this corresponds to the case where W is just the Euclidean ball, and A we interpreted in this context as a data matrix. So assume we have like n vectors in our D, so we just put them as rows of the rows of the matrix, and each vector that has a positive label we just enter as is, and if it has a negative label we enter the negation of it. And in this case, gamma, the optimal value, is exactly the margin of the data set. In another context, this corresponds to computing a Nash equilibrium. So in this context, W will be the simplex, A is interpreted as a payoff matrix, and gamma is simply the game's value. Okay, so obviously we want to compute both of these in different contexts. So this will be the most ambitious slide. I'll try to recap 100 years of research on how people solve these problems. Okay, so the first thing to notice is that you can simply swap the min and the max by the min-max theorem. And minimizing a linear function over where p is over the simplex is the same as minimizing just over the polytope, like over the vertices of the simplex, right? Because it's linear. And because this is the inner term is a min of linear functions, it's concave. So we're maximizing concave function over W, so it's quite easy. We can just do gradient descent, right? And the subgradient, like supergradient to be precise in this context, the supergradient of the min. So it's just the argument. So this has a closed form, and what we recover is the perceptron algorithm for finding a linear separator. So we know that this achieves the classic rate of non-smooth optimization, which in this context is 1 over gamma squared. Okay. So this is nice. Something typically better that you can do, which is a substantially more modern idea, is replace the min function by a smooth min. Okay, I wanted you to notice that this is independent of the size of the matrix. Something you can do even better is smooth the min. So for example, replace it by a log sum exp, and then use some acceleration algorithm that people have been developing in optimization in the last decades. And this finds a linear separator if you do it right with up to a log term that depends on the size now, but up to a log term like 1 over gamma. Okay, so 1 over the margin, so quadratically better. And more generally, you can also do this in L1 geometry and get a epsilon suboptimal point with up to log terms 1 over epsilon steps, which is the best known way in the dimension-free regime to approximate a Nash equilibrium. And in the optimization context, this was introduced by Nemirovsky and kind of reinterpreted in game theoretic sense by the seminal work of Rocklin and Sirhan. Okay, and quite surprisingly, lower bounds are pretty much unknown for these problems. And I'll try to claim now that there's a good reason for that. On one hand, what are we, I mean, lower bounds in terms of what? What does each step even involve? So in the first algorithm that I presented, each step simply needs to take the current iterate, W, and multiply A by W. Okay, and then you choose the minimal one and the minimal index and whatever. On the other hand, in the smoothing framework, if you want to replace f by some smooth approximation and take the gradient of the smooth approximation, by the chain rule, that corresponds to doing at each step something that needs to multiply a both on the right and by a transpose, or equivalently multiply a from the left. Okay? So what I want to notice is that we're comparing apples and oranges here. The first algorithm multiplies a on each step on one side, and the second one multiplies a's on both sides. Okay? So this leads to natural definitions of oracles. So we define in this work two natural oracle or axis models to the matrix, which is what it's allowed to do per step. The first one is a one-sided oracle, which just allows multiplying from one side and pulling rows out, which is what the perceptron needs to do. And the more general model allows access from both sides, so taking combinations of rows and combinations of columns as we wish. Okay? And then the oracle complexity in the style of optimization theory is just what is the best an algorithm can do over a family of matrices in terms of the number of oracle calls when it wants to solve the problem up to some accuracy epsilon. And here we are interested in the size-independent regime, like similar to the results that I showed, which don't or nearly don't depend on the size of the matrix, but rather only on the margin. Okay? So a warm-up theorem is that in the one-sided model, you can't do any better than the perceptron. So any deterministic algorithm using one-sided queries to find a linear separator needs at least order of 1 over gamma squared queries. And the proof is actually quite simple. For people who know lower bounds in optimization theory, it's very much based on Nemirovsky's lower bound, so I don't want to get into the details for the interest of time. But this theorem has already two consequences. One is that, like I said, perceptron is optimal in this oracle model, so you cannot accelerate in using only one-sided queries. So equivalently, in order to accelerate, you need to be able to multiply a on both sides. Okay. So what about that more interesting case? So we show that any deterministic algorithm using two-sided queries still needs at least order of 1 over gamma to the 2/3 queries. Okay? And this proof is substantially more involved and does not follow from previously known techniques. And kind of the reason of difficulty is because the algorithm can compute arbitrary combinations of rows and columns. So we need to somehow control all of them simultaneously. So how we do this, and a very general, without going into the technical details, is we introduce this random matrix construction, which is based on the outer products of Gaussians. And these Gaussians are kind of constructed along the way with the algorithm, which is why it only applies for deterministic algorithms. And it's easy to make sure using such random constructions that all the algorithm ever sees is 0 along its iterations. But what is hard is to make sure that with some positive probability, it actually has a sufficiently large margin, which is how you get a lower bound through a probabilistic argument. So I just want to note that this is the first lower bound for linear separability with accelerated algorithms. No lower bound, as far as we know, was known before for this general problem. Now for like the game theory application of this, great. So in the L1 setting, where W is the simplex, any deterministic algorithm using two-sided queries that wants to obtain an epsilon approximation of a Nash equilibrium still needs at least order of epsilon over 1 over epsilon to the 2/5 queries. And the proof is very much based on the previous proof technique. You just need to somehow adopt the covariance matrix to L1 geometry to satisfy the corresponding constraints on the magnitude and the margin with respect to L1 as opposed to L2, which is why we get a slightly weaker result. I will say that this problem, the best known lower bound was due to last year, and it was logarithmic in 1 over epsilon. So this is the first polynomial, like first even remotely close to the known upper bounds in terms of epsilon. So to sum up, in this work we identified 2 natural oracle models for matrix games and proved a bunch of lower bounds, which are summarized in this table, that in particular show a separation between them, which I think is kind of non-trivial, that, I know, multiplying a matrix on one side and on 2 sides is like very much not the same thing in terms of the power an algorithm can use. And there are many open problems that stem from this work. Obviously, closing the gaps is the more natural one. Extensions that we did not consider in this work to like general LP norms beyond L1 and L2 geometries, dimension-dependent regimes, which the first 2 of which I think are very plausible using our techniques, and extensions to randomized algorithms, which are substantially more difficult, and I'll be happy to explain offline why that seems more difficult. And just because people here in the room are interested in game theory, our intuition for constructing these lower bounds was very much geometric, and I have no idea how to interpret these lower bounds in terms of actual games corresponding to these matrices. So I think it's interesting to understand what are the games that actually are hard to solve, in the sense that hard to compute Nash equilibrium to. That's it. Thanks.
Thanks for the great talk. Any questions?
Do you think like your results can also give some insight into the open problem of finding like strongly polynomial time algorithm for finding Nash equilibrium? Like it's equivalent to LP. Like I'm wondering like if you can rule out certain methods that can achieve.
So in general, I think it's quite hard to relate kind of classical complexity theoretic notions such as like strong polynomial time with oracle access models. I think one of the advantages of optimization theory, oracle-based optimization theory since Nemirovsky and Yudin, is that you can actually prove lower bounds. And we know, just taking the analogous thing in computational complexity, that people don't know how to prove lower bounds, right? We don't know that P is not NP, although it seems that it must be the case. And we do have pretty easy ways to prove oracle complexity lower bounds. So in general, I feel these worlds are quite disconnected at the moment.
Thanks.
That's my impression.
I have a very quick one. Do you have any intuition for why the L1 geometry seems easier in the sense that your lower bound weakens? Or did I get that wrong?
No, so yeah, the lower bound is smaller. But I don't think that it's necessarily easier, at least in terms of current upper bounds. We don't know that they're separated even. I do know that our technique requires controlling, like the L1 margin is smaller than the L2 margin. So just in terms of if you construct this random matrix, the margin would be smaller, so that implies a smaller gap in terms of what an algorithm can do. So I don't know if this is inherent or not.
Okay, that makes sense. Thank you.
Is there any hope of getting improved? Is there any hope of getting improved upper bounds? Do you think it's fair to do
Yeah,
that?
yeah, there is, and I'll be happy to talk about that offline.
Okay, let's thank the speaker again. Next talk is by Rafael Zassolini on whether a calibration metric can be both testable and actionable.
I'm here today to talk about a simple but core insight into calibration and decision making. And we're going to start with a very common example in calibration, whether or not to bring an umbrella. So your preferences might dictate bringing an umbrella when there's at least a 20% chance of rain. Maybe for you, that's when the benefits start to outweigh the costs. Meanwhile, your iPhone estimates a 10% chance, should you or should you not bring your umbrella. So 10% is in fact less than 20%, but there's some notion that the iPhone's forecast might not be the most reliable. This is from a real Apple support thread where someone's like, hey, my iPhone says 10% chance of rain, but the hourly forecast seems to give something much higher. And so for any number of reasons, people might be suspect whether this iPhone's forecast, when it says a nominal probability level, whether that corresponds to the actual probability level. And this property of the nominal forecast equaling the true probability level is called calibration. And so this raises the question of how should we measure calibration to understand reliability in this setting? And prior to this year, in general, calibration metrics have either satisfied one of two key desiderata. Either one, they have been testable, they can estimate with data. This is a core thing you would want. If someone claims they have a calibrated forecast model, you want to be able to actually verify that with data. And then the other thing we want to talk about is whether or not a calibration metric is actionable, whether it provides a decision theoretic guarantee. And there's some judgment here in sort of ascertaining what exactly we mean here, but what's interesting is that prior to this year, these two things have mostly been in tension, but then our work and two concurrent works also released this year, and coincidentally also at Colt, which is kind of miraculous, are able to arrive at definitions that are essentially equivalent to one another. Okay, so just to add some notation to this discussion, what is perfect calibration? So we'll let y in 0, 1 be a binary random variable, e.g. did it rain or not. And we'll let f of x in the interval 0, 1 be your forecast of y. We'll say that the forecasts are perfectly calibrated if the expectation of y given f of x is equal to f of x almost surely. This is like 20% forecast equal to 20% probability. So this exact equality is in general not going to hold, and so we generalize this by just saying what's the expected absolute value difference between these two quantities. This natural generalization is called expected calibration error and has existed for a long time. More recent work has been able to show a certain way in which ECE will say is actionable, provides an actionable insight, but it also is not testable. And we'll talk more about that on the next two slides. So why is ECE not testable? So the main problem is that we cannot estimate ECE when f of x is a continuous random variable, i.e. you'll see a unique value each time. This is basically like the table on the bottom as an example. So the problem in essence is how can we estimate this conditional expectation that we need to calculate expected calibration error if we have only one observation? And because we can't do it, in essence, any way of estimating ECE in a principled way is more or less just estimating the expectation of y minus f of x. And this expectation of y minus f of x will clearly be non-vanishing, even if you have almost a perfect model, while we might hope that the expected calibration error would be vanishing as you get an increasingly good model. Some of you might be curious about binning, but binning is a complicated question of what it actually is doing in this setting. We can talk more about it offline. It's not answering the question in the way we would hope. So in what sense is ECE actionable? So to people in this room, this will actually look a lot like a swap regret. So let's suppose y in 0, 1 is binary, and the risk of f is the expected loss for f under any bounded proper scoring rule. Then we'll essentially be able to say that the swap regret is bounded above by the expected calibration error. So in essence, we're saying that ECE being small guarantees the expected loss with f cannot be improved by applying some wrapper h around it such that h composed with f has a much smaller risk. So this is a really powerful guarantee. But one thing we just might note, whether is it a feature or is it a bug, H may be a highly non-smooth and like almost nonsensical in what it suggests a user could do. Perhaps it would say you should bring the umbrella if and only f is in some union of disjoint intervals. It might not really make sense to an end user based on the original forecasts. So let's now talk about distance from calibration, which is a pretty different approach to measuring calibration, but very intriguing, which is essentially saying how close is your forecast model f to something which is calibrated. So you're thinking about projecting your forecast model f onto the space of calibrated forecast models and saying how close are you under that projection. So for reasons that aren't super obvious, but DCE is in fact a testable quantity. You can estimate it with data. However, it is not actionable for reasons we can actually see in this example, this toy example. So here the blue dots are YX pairs, and your model is some misspecified logistic regression where you're just going to have this orange line, where you're not picking up most of the signal in the data. So the DCE of this forecast model F is actually small because it is close to a calibrated predictor, which is just the unconditional mean of Y, which is just a trivial thing that is always calibrated. And so what is frustrating here, though, is that when f of x, the orange line, is at its smallest values on this right portion of the chart, the expectation of y given x is uniformly equal to 1. So this would be like a user not bringing their umbrella because the rain forecast is in the bottom quartile of things they would normally see, but it's raining 100% of the time. So people would be pretty frustrated with this property of a forecast model. And so this is just illustrating a way in which this other calibration metric is not really relevant for the decision-making problem itself, depending on how people are making decisions. And this exact problem is what motivates our definition of cutoff calibration error. So we're essentially assessing calibration over ranges of predicted probabilities. So we're trying to find a worst case interval subset of 0, 1, and saying when f of x is in that interval, does the expectation of y differ very much from the expectation of f of x on that interval? And then we're also scaling by the probability of f of x lying in that interval. Because we're taking the supremum over all intervals, we're essentially ensuring validity for all possible downstream users and all possible thresholds that a user may use to make their decisions. So cutoff calibration error is in fact testable under this simple plug-in estimator where you're just replacing the population expectation with the empirical mean. And the reason why this plug-in estimator will work is because we're essentially taking the supremum over a low complexity class object, which is intervals. And so the in-sample supremum won't differ that much from the out-of-sample supremum. And so that's how we're able to achieve the parametric rate here. And then cutoff calibration error is actionable in actually a pretty interesting way. So for people in this room, this is kind of tantamount to a phi regret over the class of monotone functions. So this theorem is essentially the same as what we saw with expected calibration error. However, instead of taking the infimum over all measurable h, we're taking the infimum over all h that are monotone. So what is this saying? It's saying that I think the chart on the right is a pretty good way of understanding this, which is your original forecasts are the x-axis, and potential transformed forecasts are this y-axis. So the identity transformation, treating probabilities you see from the iPhone at face value is just this green line, the identity transformation. But some people might want to add a margin of safety. Even when you see 0% on the iPhone, you might treat that as a 5%. When you see 10% on the iPhone, maybe you treat that as 20%. And so when it comes to the decision threshold of 0.2, this might mean if you're adding a margin of safety, you might actually bring the umbrella when you see a forecast below 20% just because you're adding this margin of safety. So this is an example of a monotone transformation. And what this proposition on the left is saying is that when cutoff calibration error is small, there's no point in doing any sort of monotone transformation. It would suffice to just do the identity transformation. You should treat the probabilities at face value. All right, so in summary, we talked today about how cutoff calibration error and these related metrics in recent works is able to satisfy an appealing middle ground between DCE and expected calibration error. Thank you all for listening.
Thanks for the great talk.
Hi, thanks for the interesting talk. I guess I was curious how this relates to other distances, like say smooth calibration, which is also sort of testable and useful for loss minimization.
Yes.
How does this fit into that picture?
That's a great point. So smooth calibration is actually equivalent in some sense to DCE. So it is able to, you are right, you can estimate it with data. but we would say it's not actionable in the sense that unless users are smoothly responding to forecasts, there won't be some sort of decision theoretic guarantee. One may argue, and that's something that some people might quibble with, is maybe in practice users do smoothly respond to a forecast, but that's a sort of a question between people. I usually see people just make an arbitrary threshold, and they're not even necessarily considering it too much, like is it close to the threshold or not.
All right.
So in your definition of actionable, you have this constraint that the function needs to be monotone compared to the stronger notion of actionable that existed previously. Is there some kind of an impossibility theorem that says that if we stick with the strong notion of actionable, it will not be possible to be both testable and actionable?
I think that emerges from sort of the essential proof for how to prove actionability in the swap regret sense, that you essentially need to be bounding expected calibration. It can only be really bounded by expected calibration error. So I think you are, in essence, running into a hardness result where in order to bound swap regrets, you have to have something which is not testable in the continuous f of x regime.
Thank you.
Okay, let's thank the speaker again. The last talk of this session will be on corrupted learning dynamics in games.
Hey, thanks for the introduction. I'm Tere, and I'd like to give a talk about corrupted learning dynamics in games, and joint work with Shinji and Hypen. So I'd like to start from the simplest form of learning games, learning in two players of some normal form games. This game is characterized by an unknown payoff matrix, which is an mx by ma matrix with entries between -1 and 1. And here, mx and my are the number of the actions of x and y players. And in this game, for its time step t, x player selects the strategy xt, which is a probability distribution of its action set, and y player simultaneously selects yt. And then x player observes the expected reward vector gt, which is ayt, and then y player observes the expected loss vector lt, which is a transpose xt. And finally, x player gains a payoff of xd transpose ayt, and y player incurs a loss of the same amount. So this is a zero-sum game. And the goals of x and y player is to minimize the regret without knowing the payoff matrix A. And using the gradient vector gt and lt, we can see this problem as an online linear optimization over the probabilities index. And I guess most of you know that there is a deep connection between no-regret learning dynamics into players of some games and Nash equilibrium. Specifically, let x per t and y per t with the average price of x and y players over large t rounds, then its product distribution is an approximate Nash equilibrium, and its approximation ratio is upper bounded by the sum of the regret divided by large t. So from this result, we can see that if both player uses the standard online convex optimization algorithm with square root t regret, we can get 1 over square root t convergence rate to Nash equilibrium with uncoupled learning dynamics. So is this optimal? It turns out to be no. We can improve this convergence rate by using the, for example, optimus catch algorithm, which is a variant of the very well-known Hatch algorithm. It simply double counts. It uses a last iteration twice in exponential weight format. And what's known in the literature is if both players free follow optimus catch with a constant running rate, the regret of both players can be upper bounded by a constant, which implies an order or 1 over t convergence rate to Nash. But but the important thing here is that we assume that both players completely follow optimistic hedge. So we are wondering what if the opponent does not follow this optimistic hedge. And of course, continuing with the optimistic hedge with a constant running rate lead to a linear regret. So one solution which is famous is to monitor the gradient variation, and it exceeds the threshold and switch the algorithm with a worst case regret obscurity. So to summarize, but this solution has an issue, which is discontinuous behavior of the leaglet. So in the honest regime, yeah, let's consider the figure where the vertical axis is the regret of X player and horizontal axis is the amount of deviation by Y player. And what we know is that if in the honest regime, where every player follows the given algorithm, we can get the regret of X player can be upper bounded by a constant, but that as soon as the amount of deviation by F player exceeds a certain threshold, the regret of X player jump to the square root T. So this is undesirable. So this brings us research questions. Can we adapt to deviation of the opponent player from the given algorithm? Or more broadly, can we characterize regret or its convergence rate to a Nash in such corrupted games? And what we did is we established a framework of corrupted games where each player may deviate from the given algorithm. And also we specifically derived regret upper and lower bounds for 2 players of some games, and also for multiplayer zero sum games. So let me formulate corrupted regime in 2 players of some games. In the setting for each time step T, a prescribed algorithm, for example, optimistic hedge, suggests the strategy to X hat T and Y hat T to each player. And then, but each player does not have to follow these suggestions. X player may select the strategy XT, which can be different from X hat T, and Y player selects YT instead of Y hat T, possibly depending on the past observations. And then the rest of the procedure is the same as a non-corrupted case. X player observes the expected reward vector, and Y player observes the expected loss vector, and the payoff and loss are determined based on the actually taken action. And we use she hat X and large she hat Y to denote the cumulative corruption of strategies. And we also consider the case there is a corruption in observed utilities. That is, X player observes the corrupted reward vector G tilde T instead of GT, and Y player observes the corrupted loss vector L tilde T instead of LT. And payoff and losses of each player is decided based on the corrupted or non-corrupted vector, gradient vector, depending on the problem setup. And we use sheet tilde X, large sheet tilde X, and large sheet tilde Y to denote the cumulative corruption of observed utilities, and use large sheet X and large sheet Y to denote the total the corruptions for each player. And one important remark here is that corrupted regime with no corruption at all correspond to the honest regime, where every player exactly follows a given algorithm. And corrupted regime with arbitrary deviation by Y player correspond to the adversarial scenario for X player. So this is kind of interpretation for honest and adversarial regime. And so let me explain our algorithm for the corrupted regime. So what's used in the literature is an optimistic hedge with a constant running rate. That is basically for honest regime. Our algorithm is very simple, using optimistic hedge, but with adaptive running rate. This choice is very similar to the very well-known Adagrad choice, but this is choose to the running rate can be upper bounded by the running rate is just has to adjust it to be upper bounded by an absolute constant. So here's our main result. With optimistic hedge with a constant running rate, in the honest regime, the regret is upper bounded by a constant, and in the corrupt regime, which can become square root T. But our upper bound, our algorithm can achieve slightly better, slightly improved regret upper bound in the honest regime, and adaptive bound of square root of deviation by another player in the corrupt regime. So if there is no any corruption of those utilities, the regret of X player is upper bounded by square root of deviation by opponent player plus the linear term of its deviation. So this smoothly interpolates constant regret in the honest regime and square root regret in the adversary scenario. And this incentivizes the player to follow the given algorithm because any deviation by opponent player encounters only a square root loss, square root penalty, but deviation by player its own self lead to a linear penalty. So let me briefly explain the lower bounds for this guarantee. So if corruption occurs only X players observe the utilities, the regret with respect to the corrupted gradient vector can be upper bounded by square root c tilde x log mx. And there is a matching lower bound. That is for any running dynamics, there exists a corrupted game with corruption on gradient vector at mod c tilde x, such that regret is lower bounded by square root c tilde x log mx. And the second lower one is about players' own strategy deviation. If corruption occurs only in X-related strategies, the regret can be upper bounded by the linear term of its deviation. And there is also, there's again a matching lower bound. For in running dynamics, there exists a game with deviation of X player upper bounded by C hat X, such that regret is lower bounded by the omega of C hat X. And there is also a lower bound for opponent's strategy deviation. I skipped the detail due to the time constraint. And a final result I'd like to introduce here is extension to corrupted multiplayer zero-sum games. We specifically consider swap regret, which has a deep connection to correlated equilibrium, and okay, as in the case of two-player zero-sum games, and it is known that we can get log t regret, which is phosphate, in the honest regime, and we can get square root t in the corrupted regime in the existing work. And using optimistic FTIL with adapting running rate, we can get the same regret upper bound in the honest regime and adaptive upper bound in the corrupted regime. A square root s hat is the amount of deviation by the other players. And key technique, which I'd like to explain briefly, is the stability analysis of stationary distribution of the Markov chain, which is a standard approach to minimize swap regret under optimistic FTIL with adaptive running rate. Thanks. There are many directions for future work, and that will be interesting. Thank you very much.
For the great talk. Maybe one question before we break?
I think there's a similar adaptive learning rate in one of the Racklin-Sudharan papers to the one you showed. Do you know the difference between them?
Sorry, could you please repeat again?
I think in one of the Racklin-Sudharan papers, there's an adaptive learning rate that looks kind of similar to what you're using. Do you know how they're different, or if they're the same adaptive?
Yeah, probably the same, because the choice of learning rate itself is very, standard in the literature.
Okay, if there are no other questions, let's thank the speaker and thank all the speakers for a fantastic session.
Sorry, just quick information for these afternoon activities. Please arrive on time, especially for the treasure hunt at 2:30. And also, if you go to the boat dinner tonight, please arrive on time because the boat will go. Yeah. If you attend to the Women in Business meeting, it is in the opposite building just after the exit. If you are looking for lunch, you can go on the online schedule and tap on lunch, and you will be given several recommendations for restaurants around the corner. Thank you.